Yeah. Ooh, okay. Well, that was a little technical difficulty. Hope it. I don't know why it's not going to that one. Okay. How's everybody doing? I know it's cold, it's freezing, it's terrible. All right. So, at the end of class last time, you all did an exercise about putting our electrons in orbitals. Just shut my phone off. Sorry. Um, and uh, and so now, with what we did at the end of class last time, and you could refer to this sheet. This has all the orbitals that I've showed you already. Um, we have basically a set of orbitals. And we know we can use them. We could put electrons in them, and we can study atoms that have more than one electron, which is like most of them, except hydrogen, right? So, we have these orbitals. We have the 1s, the 2s, the 2p, blah, blah, blah. We kind of know what they look like. Those little like electron apartments. We know that you could put 2 electrons in each one. And so what we're going to work on first is for multi-electron atoms. How do we putting electrons in these orbitals? And as you might imagine, like everything in this course, there are certain rules that we have to go by. This rule is called the building up principle. It's actually in German, the Aufbau principle, but that's all right. We always use the building up principle. That's what it means. And it's basically the idea that you start with the nucleus. So if you want to figure out where the electrons are in sodium, you would look on your periodic table. You would find that sodium has a Z of 11. What does it mean that it has a Z of 11? What's in the nucleus if the Z is 11? How many protons? 11. Okay. So you start with the nucleus, with the number of protons in the nucleus. And then what you do is you place electrons in these orbitals, and you do it so that you fill up the lowest energy orbitals first, because you want your atoms to be as stable as possible. Okay. So this kind of brings up a problem right away. Because in hydrogen, what we've studied so far, we know that the energy depends on that n value, the n quantum number, which could be n equals 1, 2, 3, etc. And in hydrogen, you have an electron in the lowest orbital. You could put it in a different orbital, but that would be an excited state, right? You can excite these electrons with light. But for the ground state of hydrogen, you would want to be putting that. Can I move that thing? Putting that in the lowest energy orbital possible. So we know for hydrogen that the energies only depend on n. In fact, we even have an equation for it. Remember, it's that minus k times 1 over n squared. But that is not the case for multi-electron atoms. It's more complicated than that, of course. And, this course is, just introductory chemistry. Can I move this thing? It's driving me crazy. Oh, look at that. Very nice. Now you get to see my kids at the beach like 20 years ago, my kid and my nephew and niece. All right. So how is it more complicated? All right. So you have this figure. I believe I gave it out with the packet last time. Yes. It's like on the third or fourth page. So if you want to write any notes on it, you can write it on there. And what I show here, these are the energies of the different orbitals. This is for the hydrogen atom. And you'll notice that here we have n equals 2, but we have a 2s and a 2p orbital. And notice they are at the same energy. So all n equals 2 orbitals have the same energy. So that is to say, if I took my 1s electron, my low out of the 1s, and put it in the 2s, or put it in the 2p, the result would be the same energy. Similarly, you could see that all n equals 3 orbitals have the same energy. But now, when we look at multi-electron atoms, we see that this is not true, right? We have a difference in energy here. So what's going on? And here we have this difference in energy between 3s, 3p, and 3d, okay? So, you know, what's going on here? All right, because it's not the same anymore. So if we're going to put in our electrons into orbitals lowest energy first, we need to understand and know what the orbital ordering is in terms of increasing energy. Okay, so here's a fact I'm going to tell you. The fact is that if you're filling a 2s or a 2p orbital with electrons, it must be that the 1s is already filled, right? Because that's a lower value of n, that's going to be closer to the nucleus, that's the lowest energy. So the fact is, if you're filling the 2s or the 2p with electrons, it must be true that the 1s is already taken, right? Already filled, which I didn't spell right. Okay. And that's true. And what happens is that the electrons that are already in the 1s orbital, they influence the energy of the 2s and the 2p. It changes the charge that is actually felt by an electron in the 2s or the 2p. So it turns out that the 1s electrons affect the energy of the 2s and the 2p orbitals, and it affects them differently. So we have this thing so and I'll tell you more about this, but the charge, the nuclear charge that's actually felt or experienced by 2s or 2p electrons is not the same due to the influence of the 1s electrons. Okay, so we have something I have to talk about called the effective nuclear charge. So we all know what the nuclear charge is, right? The actual nuclear charge is Z. It's just the number of protons in the nucleus with a plus sign. But the effective nuclear charge, which we call Z effective, is the charge that's actually felt by the by electrons in a given orbital. Usually we care about the outer electrons. So this is the charge actually experienced by electrons. And it turns out that this effective nuclear charge is equal to the nuclear charge minus this S, which this S we called a shielding. How do you spell shielding? Not that way. A shielding term or screening term. Now, what's it from? Okay. Well, you have to imagine that if you have a nucleus with a plus charge, and then you have some electrons in a 1s orbital, and that those are filled with 2 electrons, and now you come in and you want to put electrons either in a 2p or a 2s orbital, that the presence of the electrons here is going to partially cancel some of that nuclear charge. It's going to partially screen out some of the nuclear charge. So this is a partial cancellation by the 1s, by other, let me just say by other electrons. Okay, so any electron in an atom is not going to experience the entire nuclear charge. It's because of the other electrons, and the other electrons will partially cancel some of that nuclear charge. So all electrons cancel out some nuclear charge. But electrons that are in between a given electron and the nucleus, they do the best job of canceling it out. That makes sense, right? Because those electrons are in between, and so that nuclear charge is like, it's not all getting through. It's getting partially canceled by the in-between electrons. So I'm going to say that electrons in between a given electron and the nucleus do the best screening job. And so that means they will have a higher S value. This is the thing that's subtracted. So what does that mean as far as the 2s and the 2p, and which of those fills first? So it turns out that because of this, I'm going to show you a picture to show you why. Because of this, the 1s electrons actually do a better job screening the nuclear charge from the 2p than from the 2s. So the 1s electrons screen 2p electrons more effectively, and it's because of the shape of the orbitals. So as a result, the Z effective, so remember what that means, Z effective is Z minus S. If S, the 1s electrons screen the 2p more effectively, so S is greater, that means the Z effective will be smaller. And it's larger for the 2s. So here's my next question. If the effective nuclear charge felt by the 2s electron is greater than a 2p electron, which will have a lower energy and fill first? What does nuclear charge have to do with energy? If you have a greater nuclear charge, you have a greater attraction, right? Attractions stabilize, just like bonds stabilize. Attractions stabilize. So the 2s with a larger effective nuclear charge has a lower energy and fills first. Which is why our orbital order is 1s, 2s, and then 2p. Now, to tell you why the effective nuclear charge is greater for the 2s, I'm going to show you a slide that has in it a picture of like the cross section of the 2s orbital and a picture of the 2p orbital. So what this is taken from earlier. I had some slides. This is the 2s blown up. Okay, so I think you should just like not even bother with that. Let's just look at this. This is the cross section here of the 2s orbital. And now remember, the 2s has this interesting property that it has this region of zero probability. That's the white here. That's a node. But then it has some intensity right in the center here. Okay, that the blue is where the bluer it is, the greater the probability of finding the electron. Okay, so now if I take a 1s orbital, which is about this size, and I superimpose it here, okay, and I superimpose the same 1s orbital over here, and now you have to ask yourself, for which of these orbitals is the 1s more often in between the bulk of where you would find that electron and the nucleus, which is right in the center. When electrons are in between the nucleus and a given electron, they cancel out the most nuclear charge. So which is going to cancel out more nuclear charge here? In the 2s, you've got this region in here where you have some probability of finding that 2s deep within 1s territory. On this one, you see that the 1s is almost always in between where the electrons are in the 2p mostly and the nucleus. So the 1s does a better screening job on the 2p orbital than on the 2s orbital. So here I show the picture. It's got the 1s superimposed. And what you could see is that for the 2p, the 1s electrons are almost always in between where a 2p electron is and the nucleus. So the 1s electrons do a better screening job. They do a better job at canceling some of that nuclear charge for the 2p. And so what that means is that the Z effective is smaller for the 2p. So remember, Z effective is Z minus S. S is larger for the 2p shielded by 1s. Here you have a region where the 2s has some probability very far into 1s territory. So that means that the 1s does not do as good a screening job. So S is smaller. And since Z effective is Z minus S, this is smaller. So Z effective is larger. Sorry about the handwriting down here. And if you want to read about it, that's explained here. So the bottom line is that the 2s orbital has a lower energy and fills first. So we have the order that we would fill the 1s first, then we'll fill the 2s first, second, and then the 2p. Okay? Now, there's considerations very similar to this all along as you go and you try to fill orbitals with electrons. Yes. So these types of shape considerations and shielding considerations are complicated. You can imagine they get much more complicated as you go further along on the periodic table. So chemists have devised a rule. There's always a rule, right? We call it the N plus L rule. That sort of puts this all together so that we don't have to figure out about the screening for every single case. And this is how it turns out. You fill orbitals with the lowest combined value of the sum of N plus L. Remember those two quantum numbers. So that means that the L has an influence on the energy. L, if you remember, is what distinguishes between an S orbital, a P orbital, a D orbital, right? S is 0. Sorry, S means L is 0. P means L is 1. D means L equals 2, etc. So you know, if you want to know which fills first, just add up n plus L and figure it out. Or there's an even better way, which I'm going to show you, which is if you make this kind of funny chart, not really funny, but you start with 1s and you write all the s orbitals going down. Go. Okay. And then on the 2 column, you put 2s, then you put 2p. Then you put 3s, 3p, 3d. 4s, 4p, 4d, 4. Oh, you don't need, I guess you could put 4f there. Wait. No. I don't think you need to put it there. But anyway, here. So we just do this. Just make this chart, this funny chart. That's enough. And then you draw diagonal lines going this way. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. This tells you the order. Okay. Maybe I should have put 4f in here. 6s. Let me see. Let me look at the periodic table. Look up. Yeah. I should have put 4f there. Anyway, we don't fill them all this far, so we're good with this. So you could see that the order this gives is 1s, 2s. So you just follow the arrows, 2p, 3s. Next is 3p, 4s. No, wait. I can't believe this. 3s, 3p, 4s, 3d, 4p, 5s. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Okay, so if you draw your diagram nice and neatly, it's very easy to do this. Okay, so with this order, now we can start placing electrons in orbitals. And we are going to do something. We're going to write the electronic configurations of different atoms using this orbital order. So in other words, we're going to put 2 electrons in each of these things. One's going to have spin up, one's going to have spin down. And we're not going to use most of those orbitals because we're really not concerned with the elements that are very far down in the periodic table. Yeah. Yeah, it's you know, you have positive and negative charges. So if you have a positive charge over here and an electron over here, and suddenly you come in and shove a whole bunch of negative charges in between those two, it's not going to feel that same positive charge because the negative charges are influencing that and are partially screening out that positive charge, are partially canceling it. So that's what it is. It's like it can't be the same. It can't be that if you have a negative charge here and a positive charge here, that it's the same, going to feel the same thing as if you put a whole bunch of electrons in there. Well, you know, that's really a question for a physicist. Yeah, I don't know. I mean, I don't know something I could tell you like quickly. It's just not, you know. all this business about positive and negative charges is not something, you know, we run into in our daily interactions with other people. So it's not so intuitive for us, but don't feel like you're the only one that doesn't fully understand that. Anyway, so I want to show you some of these electron configurations, and I want to have you write some of them, of course, yourselves. So we start with Z equals 1. Of course, that's the hydrogen atom. So what we do is we write the symbol, we put a colon, and then we start with a 1s, and we put a 1 here. And what this means 1 electron in the 1s orbital. And another way to do it is we use the box picture, which you could either write this way, or you could put a full arrow, okay? And of course, there's room for another electron to have the opposite spin. We draw that as an arrow going down, but that's for helium. So Z equals 2, we have helium. Helium is 1s. Now we could put 2 electrons in each orbital. So we would say its electronic configuration is 1s2. And if we did it in the box form, we would write it this way, okay? Or you could use full arrows if you want. Doesn't make any difference, okay? So take out your, well, okay, let me just do a couple more. Z equals 3, lithium. So now we're going to fill the 2s, remember? Because the 2s has lower energy than the 1s. So we have 2 electrons in the 1s, 1 electron in the 2s orbital. And if I did the box form, I'd have a different box for the 1s and the 2s, like that. Okay? I'm going to do one more, and then I'm going to let you do some. You have to find this handout when the time comes. I gave it out a while ago. So this is beryllium. So it's 1s2, 2s2. And of course, the box forms would be very similar. Okay. Okay, the next one is boron. So go ahead and do boron. Boron is Z equals 5. And this handout, hope I gave it out right. Yeah, it's in the packet that has the orbitals on the front. It's the second to the last page. Looks like this. Don't you have it? Oh, I have to take it. Yeah, that's it. Yeah, it's the second to last page of the chapter 6, part 2 packet. If you don't have it, I have plenty of copies up here. Well, plenty, some. Yeah. Hi. You don't have it?
Well, this is the old one.
Yeah, it's a new one.
Yeah, right.
Oh, I thought you were coming to get the old one. That's right. All right, so boron, what do we do here? We look at our Z value as 5. So that's 5 electrons to put into orbitals. They're actually written here, lowest energy first. So this is the correct order. So you just go 1, 2, 3, 4, 5. And then you write boron with a colon. And what am I going to put here?
Are those ones that you're writing?
They're arrows to represent the plus and the minus 1/2 electron spins. Arrow up, and spin down. No, we start with the 1s, 1s2, 2s2, 2p1. That's right. Okay. That's it. All right. Okay, so the next up is carbon. But already with carbon, we're going to run into a problem. Because remember, these 2p orbitals that you have here, they're the 2px, 2py, and 2pz. And they have the same energy. So am I going to put it in like this with one up and one down? Or am I going to put it in like this, one at a time? Or am I going to put it like this? And, we don't know that yet because I have to tell you another rule, which is called Hund's rule, which says that when filling orbitals of the same energy, you fill them singly first. Where does it say? Hold on. Doesn't matter. Well, let me tell you. Okay, so you fill singly first with the same spin. So in other words, you would do it this way. 1, 2. See how those arrows are pointing in the same direction, and you're filling these 3 orbitals with single electrons first before you double up. All right, so this has a lower energy. This is what you do. So it's not this, and it's not this. It's this one. Fill singly first with spins going in the same direction before doubling up. So with that, to do carbon with a Z equals 6, you go 1, 2, 3, 4, 5, 6. And you would say carbon, 1s2, 2s2, 2p2. So in other words, when you put this together in the electronic configuration, you're not really telling it this much detail. You're just saying 2 electrons in the 2p. But if you were asked, well, what are the spins? Or show me the box configuration, then you would show me 2 parallel spins. We call them parallel when they're pointing in the same direction. So I'd like you to do the rest in this group up to neon. Then I'm going to talk to you a little bit about a shorthand notation with sulfur and beyond. So try doing those. I didn't tell you why. Yeah, there's a reason why I didn't tell you. No. No, it's just too complicated. It's beyond.
Are you able to understanding that what we're trying to grasp is a broad subject?
Oh, no.
Really want me to tell you? Okay, each of these is like a little magnet. If you make them have parallel spins, it keeps them apart from each other. So they're slightly magnetic repel of each other. Okay.
That's helpful. It helps me visualize. So
It's weird.
I'll explain it. Thank you. So these will fill 100 so this number so if I would have made I did so that has 10. So I know that that's going to be 1, 2, 3, 4. Now I'm kind of getting close to 10. So I'm going to start double. So it says these are only 1. There's 3. So I'm going to do 5, 6, 7.
Yeah, just like she did.
And I'm going back to the end. 8, 9, 10. Now I'm going to get 10. Stop.
On the road,
Now we
now
can
it's
so right. Yeah, exactly right. Yeah. Exactly. Reach 6. So like got the 3, you can just fold. Yeah. So then when you write this, right?
So I just want to point out that when filling orbitals of the same energy, you fill them singly with the same spin before doubling up. But before you go to the next higher energy one, you have to double up the spins in the lower energy orbital. So I was walking around and some people were they had this one right, but then they did this one. And this is incorrect. No, you would double up before you did that. Because the 2p is lower in energy than the 3s. Oh, well, right. Right. What? A smaller question?
How much class cut?
I think that maybe you could ask. Maybe you're going to say
No. Then you show yourself. Yeah.
yeah. So why?
Probably.
Oh, I don't think it's helpful.
This is what I had. Yeah, I just did.
Who needs a handout? Just didn't bother coming up front.
Yeah.
Yeah, it's pretty strict, right? Well, all I did was I went to the.
No, wait, I have to show you the rare gas shorthand.
Okay, so I'm going to use sulfur to show you the rare gas shorthand. So sulfur has 16 electrons. 1, 2. Okay, wants to disappear on me. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so I would write this as sulfur, 1s2, 2s2, 2p6, 3s2, and 3p4. Are you okay with that? All right, now what you do is you notice, if you look at this, 1s2, 2s2, 2p6. Oh, I should have done this. Let me finish this. I'm just going to do this so that you have it in these notes. Okay, now if you look back here to neon, neon is a rare gases are noble gases. It's the same thing. It's the last column in the periodic table. So it might be good for you to have a periodic table in front of you. There is one in this handout that's in there in that set. But anyway, the last column is the rare gases or the noble gases, and neon is one of them. And you notice here that you have a filled n equals 1 and n equals 2 shell. This is a configuration for a filled n equals 1 and n equals 2 shell. So we use the rare gas shorthand. We write that sulfur is, in brackets, neon 3s2, 3p4. Okay, so in other words, you just look for the previous rare gas and start your configuration off with the previous rare gas, and then you just go from there. All right. Now, I want to point something else out to you about that. I'm going to use this sulfur as an example to show you. These are the outermost electrons. We have a word for them. We call them valence electrons. These are the electrons in the last shell that is not filled. So the n equals 3 shell is not completely filled. So all these electrons in the n equals 3 shell are valence electrons. The electrons here, this, which is equivalent to this, right? This is the same. These are the electrons in filled shells. These are, we call these the core electrons. And these are the electrons, by the way, that do most of the shielding of the valence electrons because they're in closer shells. So they're in between the valence electrons and the nucleus. We'll be using that later. So with that, I'd like you to go ahead and do these others, or as many of them as you can. I'm going to collect like chlorine and titanium as a handout of the day on a separate paper. So just give me the configuration. You don't have to do the boxes. Just give me the rare configuration with the rare gas shorthand. And you're going to notice something. Well, just do his best. Do what you can here. Where's titanium? Oh my God, I forgot it. No, it wasn't. You put in brackets, like neon in brackets or argon in brackets. Sorry? No. Well, do the ones that do as many of the ones for the handout of the day are just the configuration, no boxes. They were, just a minute. Yeah, chlorine and titanium were the ones. But just give me this part. Row, every period, the periodic table, start to fill a different shell. First period, you're filling the end. Second Okay. So let's do these. Sodium, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Now, using the fact that the first, as you go across each period, you're filling a different shell. So you could see here that the n equals 1 shell is filled. The n equals 2 shell is filled. So you could go and look at the end of the second period and you see it's neon, and neon has a Z of 10. So that takes care of those 10 electrons. You only have one other electron. So Na will be neon 3s1. Or if you wrote the whole thing, okay, magnesium is really quite the same, except you have 12 instead of 11. So it would be neon 3s2. Yeah, what's in brackets is always in the last family, the last group, the last column of the periodic table. Those are the rare gases. So chlorine now, I'm not going to do for you because it's one of the HOD. I think you know how to do it. Well, maybe I'll do that one for you. What the hell? So if you look at chlorine, you have to go way back. You have to go way back. Chlorine is 17. So look in the rare gas column and you see you have 18. You can't use it. That's too many electrons for argon. So you go to neon, which is 10. So you know chlorine is going to be neon. And that takes care of the first 10 electrons. You only have 7 more. So this is all taken care of in the rare gas configuration. That's 10 electrons there. That's neon. And so you have 3s2, 3p5, because it's 17. Argon, now argon is 18. All of these are filled. Because it's 2, 4, 6, 8, 10, 12, 14, 16, 18. Okie dokie. So you would just write argon, right? Pretty stupid, but that's the shorthand. All right, what about calcium now? What would the rare gas shorthand be for calcium? If you go back, calcium is 20. What's the nearest previous rare gas in this column? Argon, and argon is 18. So calcium would be argon. And now argon, you see that it's in the third period. It's in the third row down. So the n equals 3 shell now is done. You're starting with the n equals 4 shell. So you're going to start with 4s2. And so calcium is 20. So that's it, because you had 18 electrons from argon and you just need 2 more. If you did it this way, you know, you'd be doing this forever, which is why I like the rare gas configuration and I highly recommend it. So that's calcium. Don't forget the 4s2. I didn't write that down. Oh, wait, hold on. Oh, I put it in the wrong place. Sorry, I messed it up. Yeah, argon is just argon. Calcium is argon 4s2. Oh, wait, did I? Oh, no. It's 20. It's 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yeah, no 3Ds.
Oh, that's the
Titanium, again, you would start with argon. That takes you through 20 electrons. You have 2 more. So sorry, 22. So you have 4 more. So argon is 18 electrons. So there's 4 more. And I think you could figure out where to put them in here. That's part of the handout of the day. Gallium. Now this is an interesting one because it's got a huge number, 31. So you'd start filling 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, 21, 22, 23, 24, 25, 26, 27, 29, 30, 31. Now, the closest rare gas is not that close, right? Krypton is 36. That's too much. So you use argon. But then after argon, you have 4s2, 3d10, 4p1. Okay, so I think that's enough of that. You get the hang of that. Now, there's a couple of exceptions that I'm not going to tell you about, and we're not going to study this semester. There's exceptions in the electron configurations for Cr, Cu, Mo, and Ag, but we're going to skip them because they're just not that important. Okay? So now we can write electron configurations for elements, so we're getting used to it anyway. And so you might just look at these things and say, oh, electron configurations, oh, they're all the same, right? What do they really tell you? Do they really give you any, like important information? And they do, actually. They give you a lot. The similarities and differences between electronic configurations of different elements kind of demystifies or helps us really understand what this periodic table is all about. So I'd like you to take this piece of paper that I gave you. Okay, and this actually, so if you take a look at this and you put the electronic configurations of these different elements that are specified. So lithium, we already did, is 1s2. Well, let's do the rare gas configurations. Helium. What do I put after helium in here? Well, helium fills the first shell, the n=1 shell. This is the n=2, so 2s1, right? What about potassium here? What's that configuration? Using the rare gas, go back to argon. And now 3, 4, we're filling the 4s shell as you go down, right? It goes n=1 is the first row, n=2 is the second. Okay, and you notice, and I'm going to go over here and do oxygen first. Oxygen, you go back to helium. What goes after here for oxygen? Two S, yeah, 2. What oxygen is 8, right? Helium takes care of 2 of them. You have 6 more, 2p4. Now, what about sulfur? Neon. Three S2. Yeah. And so this is no coincidence here. You have elements in the same group or family or column in the periodic table. Notice this is the outer electrons. It's different shells. You could say ns1. They all have one s electron in their outer shell. Okay. Over here, all the elements in this group 6A end in ns2, np4. They all end up with 2 s electrons and 4 p electrons in their outer shell. Now, here's the thing. Chemical reactivity is largely determined by the number and type of outer shell valence electrons. So long ago, we started learning that if you have elements in the same column, they have similar chemical reactivity. But now we know why. Because they have the same number and type of outer shell electrons. So what can you conclude about the outer electrons of elements in the same group of the periodic table? So what do you think you should write here? The same number and type of valence electrons. Yes. So that's what you should write in here, something like that. Remember, the groups are going down. Those are columns. And that's why they have similar chemical reactivity. You know, that's a complicated mess of these transition elements here. It's a little harder to decipher. You have to take inorganic chemistry to learn about that, I guess. Okay, so the next thing I want to talk about is the periodic table. So I gave you this as a handout, but I want to make sure, you know, this really is going to help us understand. This is a special periodic table, right? It's not what it has written on it is what the outermost electrons are as you go across and down the periodic table. But I want to point a few things out here. First of all, and I've said this before, I'm just going to say it again. As you go across, and so we're looking for patterns here in the periodic table. And there are many of them. Okay, first, as you go across the periodic table, each period starts with filling the next shell. So let me write that down. Each period, and that's going across, starts with filling the next shell. So here you're starting to fill the n equals 1. Here you start to fill the n equals 2, n equals 3, etc. Okay. And each period ends with filling that shell. So here you end with filled n equals 1 shell. Here you end with a filled n equals 2 shell, filled n equals 3 shell. Okay. And now when you go down a group of the periodic table, as I have just said, you have the same outer shell electron configuration all the way down. What this is showing is the valence electrons. Here going down, you have the same outer shell electron configuration. So all elements in groups have the same valence electron configuration. You can take here, nitrogen, 2s2, 2p3, 4s2, 4p3, etc. Okay? And that is why they have similar chemical behavior. Now, there's plenty of other things to note on here as far as patterns. So the fourth period, let's look at the fourth period. So the fourth period starts with filling the 4s right here. You have 4s, 4s2. Then these fill the 3D. So the transition elements here are filling the d orbitals. Okay, so the fourth period starts 4s2, but then it goes to 3d, and it fills those 10 places. Now, why 10? How do, you know, the reason there's 10 boxes here is because there are 5 3d orbitals. Remember, for d, we have L equals 2. So we have -2, -1, 0, 1, and 2. That's 5 d-type orbitals. So that's room for 10 electrons. And that's what the middle of the periodic table is doing. Here it's filling the 3D. Here it's filling the 4D, the 5D, the 6D. And it's always 10 wide. Okay? Then we have a little break over here. Remember, these are the lanthanides and the actinides. And what happens is we take a little detour down here. And you'll notice here you're filling the F subshell. And the F subshell, so this is in period, the 6th period. You start by filling the 6s. Okay, but then you go to the 5d. And then you skip, if you look at the chart, let me go back, let's see. So if we go back, let me show you this again. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, d. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, after 6s. You don't have to copy this, but I just want to show you this. So you'll notice 6s, then 4f. Oops. Oh, come on. Just when you're in the middle of something, it wants to do this to you. I don't think I'm sharing anymore. Wow, I have 2 of them open. That's great. Close one of them. Of course, I closed the wrong one. Okay. Oh no, it took my diagram away. I'm just going to go back then. Sorry. Oh my God, really? Are you kidding me? I don't know. Technology. It's better than it used to be. Still not great. It's going to do the same thing. Yay. Okay. So it's 6s. After 6s is 4f. This is way higher than I'll ever ask you to do an electron configuration. I don't know why I'm spending all this time on this, but it gives you a really good idea of what's going on in the periodic table. So in the 6th period, you cut down to filling the f orbital. So here you see they're filling the 4f, and here you're filling the 5f, except there's a few exceptions. And the F shell, the F subshell, remember now, D was L equals 2, F is L equals 3. So that means there's -3, -2, -1, 0, 1, 2, and 3. There's 7 orbitals. So that's enough for 14 electrons. And if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, that's what those F shells are doing. That's what's down on the bottom of the periodic table. So as you go across each period, you're starting with a new shell, you're ending with that shell. You do make some detours. You do have to go from 4s to 3d and then back. So this is 4s, this is 3d, and then back to 3p. Here you're filling the 5s, the 4d, the 5p. But more or less, as you go across the periodic table, you're basically adding electrons into the same shell or a shell very close to it. As you go down the periodic table, you're adding entire shells. So you're adding a whole new shell so that your outer electron configurations are all the same as you go down the periodic table. So let's see. So let's focus on some simpler things right now. Okay, let's look at what's light blue on that diagram that I gave out that doesn't have any color. But this light blue, it labels it the S block elements. Those are the first two columns in the periodic table. So we call this the S block. And so these are the first two groups of the periodic table. And for these, the outermost electrons, which are the valence electrons, are the two 1s electrons. It can be, the first group. So group 1a and this, I should say, are s electrons. So the 1a ends in ns1. You can see 1s1, 2s1, 3s1, etc. Group 2a ends, the electron configurations end in ns2. Okay, so remember I told you about chemical reactivity having to do with these outer electrons. And I could give you a very concrete example. And here it is. What ions form from group 1? Well, they're actually cations, right? So you get a +1 ion. So take lithium, which has an electron configuration, helium 2s1. And now you remove an electron and you end up with a positive charge, and the lithium ion has the configuration that is just helium because this electron is removed. And this happens for every single element in group 1 of the periodic table. Sodium. Yeah, I just love that door. I was talking to a bio professor the other day, and I was telling him I was teaching in this classroom, and he says, don't you hate the doors in there? and I said, no, I really haven't noticed that, ever since he said that. Every time someone comes or leaves, I hear the door go clonk, clonk, clonk. It was really funny. Anyway, don't worry about it. So you could see that every single element, right, in that first column of the periodic table, it ends in, ns1. That electron gets taken away. You make the ion, a single positively charged ion, and it ends up with this rare gas configuration for the ion. Okay, you could see that it's similarly. So all of these, all group 1a elements form +1 ions. And they attain what we call the rare gas configuration. You could see similarly, group 2a. Okay, so let's take a look at magnesium. What's the electron configuration of magnesium? You look on the periodic table, you can look on this thing too, because it gives it to you. But magnesium is at the beginning of the n = 3 shell. It's filling. So you could go back to neon, and it's filling the n = 3. So it's neon 3s2. When it loses an electron, it forms magnesium 2+. So both of these electrons have been taken away. And it's just neon. It's the rare gas configuration. And the next one down, calcium, similarly. It's a 4, not a 3, sorry. Take away 2 electrons. Again, it's a rare gas configuration. So for all of the elements in the group 2A, they lose 2. Oh, sorry. I had 2 arrows here. Lose 2 electrons to form +2 ions and attain the rare gas configuration. So that's the S block. Let's look at the P block. So again, if you go back to this periodic table I gave you, over here, the pink ones, this bunch here is the P block. And you could see that, because here it shows the electron configuration of the valence electrons, and they're all filling up the P orbitals, filling up the 2P, filling up the 3P, filling up the 4P, etc. So that's what happens as you go across the periodic table. Okay, so let's go back to here and look at the look closer at these P block elements. Here we go. And you could see going down, let's take a look at the halogens. This is group 7A, we call it the halogens. Salt forming, it's from the Greek, of course. Anyway, as you go down here, you see that you are filling, that the halogens end with rare gas. This is they always have a configuration with a rare gas, and then you have NS2, NP5. They're all like that. 5s2, oops, wrong one. Next one, this one. 5s2, 5p5, 3s2, 3p5. Okay, so fluorine, for example, is helium, 2s2, 2p5. Now, what happens to fluorine? Okay, well, it has these, it needs 2 more electrons to have a filled shell. It gets 2 extra electrons, so it accepts 2 electrons from somewhere. Sorry, 1 electron. Yeah, sorry, it needs 1 electron to have a filled shell. And it ends up being fluorine with a negative charge, helium, 2s2, 2p6, which is actually neon. So again, it's gained 1 electron to form a -1 ion with a rare gas configuration. That's Ne, okay? And every single element in that column, in that family, does that. If I take Cl, that's neon, 3s2, 3p5. It accepts 1 electron to form chlorine with a negative charge, which is neon. Wait. Yeah, neon, right. 3s2, 3p6, which is argon. So it attains what we call a rare gas configuration with a -1 charge. So all elements in that group do that. If we just take one other group, group 6A, that's the oxygen group. Oxygen, you can see all the ones here end in 2s2, 2p4, or 3, yeah, NS2, NP4. Well, all the elements on the right side of the periodic table gain electrons. Well, the ones on the very right, yeah. Except for the noble gases, which like staying just where they are. So oxygen starts out as helium, 2s2, 2p4. It gains 2 electrons. So it becomes O2 minus helium, 2s2, 2p6, which is really neon. Okay, so it gets that configuration. And this is true of all the elements in that group of the periodic table. All elements in group 6A gain 2 electrons. So they form a -2 charged ion. And they attain the rare gas configuration. They all do that. Okay, so you can see that there are very nice patterns that appear as you go across the periodic table and down the periodic table. As you go across the periodic table, let me just say again that you're adding electrons to more or less the same shell. Now there's slight dips at times, but it's more or less the same distance from the nucleus. So we just call it the same shell to try to be sort of general about it. Otherwise, we can be driven crazy. That's what happens as you go across the periodic table. As you go down the periodic table, you basically add entire shells. But the elements all have the same outer shell electron configuration. Okay. You also notice that on the left side, periodic table, the left side, these elements lose electrons. They form positively charged ions, cations, and end up with a rare gas configuration. And we notice that on the right side of the periodic table, they gain electrons. They form negative ions, anions, and they also get the rare gas configuration. So I guess the next thing that we really need to investigate is why do elements on the left side of the periodic table lose electrons? And why do they gain electrons on the right side of the periodic table? And why do they stop at the rare gas configuration? Is it kind of magical? You know, what's the deal? And, you know, normally in chemistry, like magical things don't really happen. That's not quite the way it is. Although it seems like magic sometimes, but normally it has a lot to do with energy. You know, what's the most stable thing? What's the less energetically expensive thing to happen? And there are some properties that we learn about in this class that vary as you go across the periodic table, down the periodic table. If you remember, the title of the chapter in the book is something like electronic properties and periodic properties is one of the things they say. These are properties that vary as you, in a very understandable way as you go across the periodic table and as you go down the periodic table. And we're going to be talking about these because they really help us understand why elements on the left of the periodic table lose electrons while elements on the right side of the periodic table gain electrons, and what that has to do with energy. So there are a couple of quantities that we're going to be talking about for a little while, and I want to just tell you a little bit about what they are. So one of them is called the ionization energy. And this is the energy that's required to pull an electron away from an atom. Now, why do you think energy would be required to pull an electron away from an atom? Yeah. That's right. Even though there's other electrons around which repel a given electron, the dominant force is the force of attraction of that electron to the nucleus. So I'm going to say the dominant interaction is the electron attraction to the nucleus. So this is why it requires energy to break that attraction, right? To pull an electron away. Okay, so we're going to learn somewhat about ionization energy. That's one of the things. Just a little introduction there. Another thing we're going to learn about is called electron affinity. And electron affinity is the energy that is released when an atom gains an electron. And again, the reason why energy is released is because the dominant interaction is with the nucleus, which is an attraction. So again, the dominant interaction is the electron to the nucleus. And since it's an attraction, is between the electron and the nucleus. It doesn't let me erase. I don't know why. Okay. So this stabilizes. And so that means it's a lower energy. Energy is released when this happens. Okay. So these two things are going to be the two energy properties that we're interested in. But the thing is, they depend on other properties. And what they depend on very much is something which I've already talked to you about. And this is the effective nuclear charge. These depend on the effective nuclear charge. Okay. So what you need to understand is what happens to the effective nuclear charge as you go across and down the periodic table. Okay, and now understanding this is a bit of a tough question for general chemistry, but I have a way of making it pretty simple. Okay, so I'm going to explain my way. I'm going to simplify what is pretty complicated. Okay, it's not that hard. The effective nuclear charge, if you remember, is the charge on the nucleus minus the shielding. Let me take calcium as an example. Okay, calcium, here is its electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, which, as you know, we can write as argon 4s2. Now, here's what I'm going to make a couple of assumptions. Remember I said that the core electrons, so these are the core electrons, right? The core electrons here are in between the outer electrons and the nucleus. Let's assume, it's not a perfect assumption, but let's assume because we know the core electrons do a good shielding job because they're in between. Let's assume every core electron cancels one proton charge. In other words, all the core electrons do a perfect job of screening the nucleus. Okay, and we're going to also assume that the valence electrons don't shield each other at all from the nucleus. So if that's the case, then the value of S here is simply the number of core electrons. So this gives us an oversimplified but useful way of calculating the effective nuclear charge, because this we get from the periodic table. That's simply the number on top of the element. S is the number of core electrons. So all you have to do is go back to the previous rare gas and look at the Z value of the previous rare gas. And that is the number of core electrons. So let's take calcium as our example here. Okay. Argon has 18 electrons. So that means that calcium has 18 core electrons. So Z effective for the outer electrons in calcium, what will it be? It'll just be Z minus S, which is 20, that's the Z from the periodic table, minus 18, which is the number of core electrons. And so we end up with the Z effective for calcium is 2. So in other words, what this is approximately telling us, is that those outer 2 electrons in calcium are only experiencing a charge of +2 of the nucleus because of all the electrons in between canceling out most of that charge. Okay, so given this, can we figure out what happens to the effective nuclear charge as we go down and across the periodic table? All right, now I don't know it's 11:42, so it's not a lot of time, but I want you to look at this handout. It's the effective nuclear charge handout. All of this writing here is what I just explained. Okay, so we're really going to start here with the do the following. So we will write the electron configuration using the rare gas notation. We'll figure out the number of core electrons that will be equal to the number of electrons in that rare gas part of the electron configuration. We will subtract that from the Z value, the actual nuclear charge, which is Z, and find a rough estimate of the effective nuclear charge. And then I have a little mini periodic table here where we're just going to write these values in here. Now, we already did calcium and we found that it was 2. Okay, so how about if I just assign you to do one of these? Okay, or maybe, so okay, let's see, we got calcium. So before you leave, how about you try this? Can you do magnesium and beryllium? You do the same, magnesium and beryllium. Follow these instructions, magnesium and beryllium. You do sodium and carbon, okay? You do sodium and carbon. And then let's have sodium and carbon. And then everyone in the class, not two nitrogen and phosphorus, and then oxygen, chlorine, and chlorine. So pick 2 of those. Let me just, I don't know. All right, how about this row here? Why don't you do nitrogen and phosphorus? Okay. You guys do oxygen and fluorine. And everyone else do chlorine and fluorine. A total number of things. So what you're doing is you're writing is you're following a simple instruction. Yeah. Minus S, which was in R. So actually, beryllium is done as an example here. Are you clear on what to do? Yeah. Okay.
They kind of line up a little bit.
Too many of the other ones.
That's good. I love this. Where are you? How close are you? Oh, you're nice. Thank you. Okay. Oh, that's why. Yeah. That one.
So
So what do we have for answers here? Beryllium was done on the chart. Beryllium is already done. Magnesium. What did you get for magnesium? 2. Sodium. Carbon. Nitrogen. Oxygen. So what you can see, what emerges here, and I'll explain it in words next time, is as you go across the periodic table, Z effective increases. As you go down the periodic table, Z effective is the same. All right, we'll go back to this next class. If you want to hand that chart in, that whole thing done for special problem credit, I will give it to you. The effective nuclear charge exercise. Yeah, but it has to show all the work.
We have to have the no.
No. Next time.
Is that due Tuesday?
Next time.
Which one? For Tuesday?
Yeah, Tuesday. Thank you for the HOQ. Thursday. You gotta get it ready here.
Yeah.
Hold on.